In this lecture, we are going to talk about intermolecular forces and introduce the concept of them. In the next video, we'll walk through each one in detail. So let's start. We recently discussed bonding in the previous class, and we talked about how bonds will arise from the attraction between valence electrons on one atom to the nucleus of the atom they are a part of, and then another nucleus of another atom. And so these valence electrons get attracted to two different nuclei, and they kind of like overlap in a way. And so we think of it as being shared, that two nuclei are sharing attractions to electrons. When really we just have this little negative charge that gets close enough to a second positive charge that it's like, oh, I'm attracted to both of these. This is great. So this is kind of a fundamental force where we have opposite charges attracting one another. And intermolecular forces are going to be exactly the same interaction, just over a larger distance. So you might hear the phrase intramolecular forces. That is the forces that are inside the molecule, that those bonding forces that are holding it together. Where inter, with an ER, is the intermolecular forces that are between two molecules. So we are no longer talking about bonds, even though we are talking about the same fundamental forces that create bonds. And the big difference, the really big difference, is the amount of distance between the negative and positive charges that are attracted to each other. So within a bond, and I've got an example here of water. So we're looking at this oxygen hydrogen bond right here, and it is 96 picometers, right? So that's times 10 to the negative 12th. So 1 times 10 to the 12 picometers equals 1 meter, or you could say 1 picometer is equal to 1 times 10 to the negative 12 meters. All right, so tiny at the end of the day. So a bond between oxygen and hydrogen is about 96 picometers, whereas the molecules will get within 300 picometers of one another. So that's 3 times the distance, which is enough for that force to become of attraction to be much weaker. Now, this is a bond between a hydrogen, which is small, and an oxygen that isn't that big, but also one that is has an electronegativity difference that's significant. So just for reference, you can always go look at bond strength or bond enthalpy tables to get an idea of how strong a bond is, and so maybe how long it would be. But for reference, a carbon-carbon single bond would be something on the order of 154 picometers. And so our intermolecular forces we're going to see are going to need to be about 175 picometers or greater in distance. So these IMF distances will be more than 175 picometers typically. And this is hugely ballpark. Oh. And so what's going on here? What is this fundamental force? And we've talked about this hopefully before. This is hopefully familiar, but Coulomb's law. And Coulomb's law just describes so much of the behavior we see when we study matter on the atomic level, which is that the attraction of opposite charges it creates this electrostatic force, and the strength of that force depends on the magnitude of that charge. So the strength, that force goes up if my charges are like +2 and -2 that are attracted to each other, or +5 and -5. And they go down if it's just like +1 and -1, or a partial charge, which we'll be talking about, so less than 1. But so that can increase that force or decrease it, but also the distance increases or decreases that force. So you'll notice Coulomb's law has an R, which is that distance between charge centers squared in the denominator. And so as we separate these two charges that are opposite, that force, electrostatic force, decreases. And as they come closer together, it increases. And so using Coulomb's law, we can say, all right, well, if this is how we get this attraction for bonds, we're going to have the same attraction that occurs between molecules, but because the distance is greater, the overall electrostatic force of that attraction is less. And so you can think of an intermolecular force as the same type of interaction as a bond, but just on a much smaller scale. And we're going to introduce a few different types of these interactions that occur that are all based on this fundamental opposites attract, like repel idea. We're going to talk about London dispersion forces, dipole-dipole forces, hydrogen bonds, and ion dipole forces. And they're listed here in terms of increasing strength. And that means an increasing electrostatic attraction force between them. Now, these types of forces, which we'll talk about a little bit more detail here, they increase in strength as the amount of charge that is being attracted, the opposite charges, increases typically. And our distance is going to be further than a bond, but like relatively similar in this case. But when we think about comparing solids, liquids, and gases, then that distance between our particles becomes the dominant factor of how important intermolecular forces are to physical behaviors or physical properties. And so solids are typically denser than liquids, which are denser than gases. And so that solid, when it's denser, means that we're packing more mass into a smaller volume. And that means that our particles are closer together. So those opposite charges, that distance between them has decreased in the solid state. And so intermolecular forces are stronger in solids than in other phases. Now, in liquids, they're still very close, but they're constantly moving, breaking interactions and forming them. And there's a little bit more distance because the density of liquids is typically smaller than that of solids. And so increasing that distance a little bit decreases the impact of intermolecular forces, though they're still very strong for liquids. But now when you get to gases, well, I mean, gases are these particles that are so far apart that when we do calculations around gas behavior, we assume they're not interacting at all. And when we made that assumption, this is exactly what we were talking about. We were talking about whether or not intermolecular forces would have an impact on their behavior, their physical properties. And so the gas particles are so far apart that that interaction is very, very, very weak. That R is just, that distance between the charges is too great. Now, we also learned about real gases, especially under high pressure or really cold temperatures, that it actually, they do interact. When they get close to each other, they're attracted or they're repelled, and it impacts the mean free path of that particle zipping around through space, which will change the actual pressure that you would measure for the gas. So the takeaway here, though, is that intermolecular forces will play a larger role in solid behavior than liquid than gas. We're going to focus on liquids and solids and the impact of intermolecular forces on their behavior. We've already talked about gases, and we've already said, well, we'll just assume it doesn't matter. And we'll continue to assume that for now.